This talk is optimizing your app by understanding your Postgres database. I understand that from the title, what I wanted to communicate is within this talk, we're going to cover problems you face from the application users, complaints they make about performance, saying that my queries are slow, or as an application developer, you're trying to understand what are the issues which are causing the application to be slow. And then tying that back to the Postgres database. So what kind of statistics Postgres gives to you so that you can figure out what exactly is going on, what's wrong, and then also how to fix it. So a bit about myself, I'm Samay. I work as an engineer on Citus. Citus is basically an open source extension to scale out Postgres across multiple machines. So when you have a single node Postgres database and you start having performance issues and not being able to keep up with the amount of workload you're putting on it, you can use Citus to scale it out across multiple servers. I manage a team of solutions engineers. So what we do is we work with clients, application developers who come to us with like problems in their application from a performance perspective, from a scalability perspective, and they want to grow their database to several terabytes, tens of terabytes, hundreds of terabytes, while continuing to maintain all the benefits of Postgres. So I work with clients to kind of help them model their application, give them recommendations on data modeling, et cetera, to help them scale their database out. I like to include a fun fact about myself on all my slides. So I recently got married about 4 months ago. Some people are telling me that it's fun fact now and it might not be a fun fact after a while. So we'll see how long it is a fun fact. So as I mentioned, Citus is open source. You can actually go to GitHub, Citus Data Citus, and then just star us. If you like to learn more about Citus, I'm going to be around in the conference. We can have a conversation about that. But this talk is not about Citus. This talk is mainly about the Postgres, and whatever I'm going to talk about applies, all of it applies to like your normal Postgres database. So the challenge sometimes you face is relating issues and pinpointing what's going on within the database. So from an application perspective, you might be seeing slower queries. Users might come to you and say, oh, my app page is not loading as fast as possible, et cetera. And you know either through your monitoring tooling or just because of like your debugging, et cetera, you figure out that the problem is in the database. The database is what is causing the slowness. Now, how do you discover what that problem is? How do you tie the root cause? And then how do you solve that problem? The simplest way to address that is using the statistics which Postgres exposes. So Postgres actually captures a lot of stats about your data. So when you run analyze or when Postgres automatically runs analyze, it looks to capture a bunch of statistics about your data in terms of, let's say, if the user were to input this as the filter, what would the selectivity ratio be, et cetera. So it keeps tracking data about all of your columns and also about your database. It also exposes to you, captures data about activity and exposes that to you. I'm bucketing that as monitoring statistics here. So it's basically what are the queries running on the system right now? How many connections are coming into the database? Which indexes are being used? Which indexes are not being used? Which queries are doing how much I/O? All that information is actually captured in different tables within Postgres, which get exposed to you, and you can just query them as regular tables and get whatever information you need. And there is some admin statistics. If you're using a managed service, you need to care about them a bit less, but then your managed service provider needs to care about the server administration statistics. So how is replication keeping up? What's the size of the database? What's the size of different tables? So on and so forth. What I'll try to do is start from a very generic problem, which is my application is slow, and I'm sure everybody kind of gets that feeling every time. Like, I don't think anybody says my application is amazing and it's always fast and it's amazing. So we'll start from that problem. Let's say we figure out that it's tied to the database, right? How do we get there? So problem, my application is slow. Symptoms, application users are complaining about slow performance. Whatever monitoring tool you're using, it comes and points out that most of the time is going in database calls. Maybe it's like certain amount of database calls, maybe it's entirety of the database, and whatever pages they're loading, everything is turning out to be slow, right? And your page is making, let's say, hundreds of database calls. You don't know which query is slow. You don't know what exactly is going on. So how do you start from there, right? A good starting point is to look at your database's cache hit ratio. So what cache hit ratio is actually the ratio of how much is being how much of your queries are being served from the cache versus how much of it is coming from, let's say, it's having to read from disk, right? So it's a good measure of just getting a feel of where your database should be and where it is off. So for transactional apps, you don't want to hit disk for your most common operations. So you want it to be greater than 95%, ideally around 99% for your cache hit ratio for your transactional applications. Now, like depending on the application, if you have an analytics application where you're actually storing, let's say, 10 terabytes of data, buying 10 terabytes of memory is going to be expensive. So maybe there it's okay to have a lower cache hit ratio, but typically that's not the case for transactional apps. Now the question is, how do I measure this and how do I keep an eye on it, right? So throughout this talk, I'm going to cover a few Postgres tables and talk through what are the different information they can provide, and then how you can use it in turn to improve the application performance. So a simple query you can run on pgstat.io user tables. So this is one of the tables I'm going to talk about. You just count how many heap blocks were read. So from a terminology perspective, heap is actually where Postgres will store your data, and indexes are indexes. So they are not a part of the heap necessarily. So when I say heap blocks read, it's basically how many blocks were read from the heap, how many blocks were hit. So and then the ratio of that, so number of blocks hit divided by the number of hit plus read kind of gives you the ratio. So you look at this ratio, you notice that it's using the pgstat.io user tables as the source for this data. So let's look at what information that table captures. This is just an example row from that table for one of the tables I created. So like rel ID, like table, what's the name of the table, what's the ID, what's the schema, I think that's all like just standard stuff. You notice it keeps information about heap and also keeps information about indexes. So it tells you how many times your index blocks were read from like the Postgres buffer cache versus it could not find that record in the buffer cache, so it needed to go and read that record. So in addition to just getting the table hit ratio from this table, you can also get an index hit ratio. So maybe your indexes are not fitting in memory, right? And that's the problem you need to solve. So depending on both of those, you can kind of figure those information out from this table. There is also some other information such as toast. So toast is when you have very large columns, Postgres actually compresses them and stores them on a separate place. So you can also measure about that. So let's say you have a huge JSON blob in your Postgres like table, and then you want to figure out if those, like reading them from disk is the main bottleneck, right? So you can figure out from this, like get the ratios and see which one of them is kind of causing this. Like just lowering the cache hit ratio is low. So let's assume that the cache hit ratio was low. That could actually mean a lot of things, right? So it's just what that tells you is you're not able to serve your workload from your buffer cache. But why do you need to go to disk, and what are the possible issues with it? There could be multiple causes. So like the first two points talk about bloat and auto vacuum. So how many of you are familiar with auto vacuum? Okay, a few. So basically, whenever you update or delete a row in Postgres, Postgres doesn't necessarily delete it at the same time. So it just marks it as not being visible to rows coming from, like let's say transactions, which are coming after your transaction. And then later there is a process called vacuum, which comes and cleans up all those rows. So, and Postgres has auto vacuum, which automatically triggers that. So you could manually trigger a vacuum and say, okay, clean up all the rows which are not being used anymore. But by default, Postgres has auto vacuum, and you can tune it to be as aggressive or less aggressive as you need to be. And then, so maybe your auto vacuum is not tuned well enough, which is why you're not cleaning up the old rows, which is why you're getting very bad hit ratios from your cache, right? So bloat is actually that chunk of unused data. So that's known as bloat generally. So you'd say, okay, I have, let's say, a terabyte of database, maybe only 200 gigs of that is actually usable data. Rest of it is just auto vacuum couldn't clean that up. So 800 gigs is just bloat. And if you clean that up, you save up a lot of space, and only the relevant data needs to be in memory, right? maybe your queries are not optimized and you're doing a lot of sequential scans. So Postgres has like the way Postgres scans your data, it will be generally either a sequential scan or an index scan. If you have indexes on your database, it will use the index to scan the rows and only the relevant rows to your query. So let's say you have a table which stores events and you create an index on the timestamp and you run a query for the last day, Postgres will use that index to just return the results for the last day and not scan the rest of the data. So if you did not create index appropriately, maybe you're just scanning the entire database all the time for queries which are much more pinpointed, right? Most app frameworks come with like creating primary key and just the basic indexes, but if you're doing more complex queries, you might have to create indexes on your own. The other side of that problem is maybe you have a lot of unused indexes, right? So you have a lot of indexes which Postgres needs to keep up to date because whenever you insert a row, Postgres needs to insert that row into all the indexes you have on your table. And if you have a lot of them and they are not being used, that could just be increasing the total amount of data you have on your database and then not being able to, use that for the right queries. So again, I would say try to optimize your single node Postgres to the best extent. And after that, if you want to think about sharding or scaling out using Citus, that's when it makes sense. I would not suggest just as soon as I have performance problems, just look at buying more hardware and trying to solve that problem. There are certain things you can do, but after a point, it does get difficult to kind of tune Postgres, and then you can look at other technologies like Citus to kind of scale it out, right? So I'll dig into like 3 or 4 tables which will actually help you pinpoint which of these problems is going on in your database. So we'll start with the standard one, which kind of covers the entire database, which is called pgstat database. So this is, again, I just picked up one particular row for this database. It gives you quite a few pieces of information. So it tells you like number of backends, like the database name, database ID. The more important fields here is transaction commit, exact commit, and exact rollback. So it tells you how many transactions kind of were committed and were rolled back in your database. It tells you how many blocks were read versus how many blocks were hit. So we looked at that information. It also tells you kind of how many tuples were inserted into your database, updated, deleted. So a lot of times you might be kind of, you might have heard of people asking you questions like, okay, is your database an insert heavy database? Do you have a lot of updates? Do you do a lot of deletes? To find the answers to those questions, you can come here and you can actually get statistics on what, like basically what are the answers to those questions, right? So what are the use cases? Typically, what I use these tables for is find out the number of rows fetched versus returned by the queries to the database. Now, both these terms are different, and Postgres actually named these columns a bit funnily. But if you look at tuples returned, that's actually how many tuples were returned. And then fetched is actually how many which were needed to run the query, right? So maybe it returned a lot of queries, but you didn't have good indexes, and you were unnecessarily returning a lot of rows. So this ratio, if you look at this particular instance, you can see about, I don't know what that number of zeros, 367 million, I think, tuples fetched versus 675 returned. So maybe half the tuples you actually were returned, those didn't need to be returned. So you could have optimized that by putting indexes on it, for example. Another example is how to find the insert update delete ratio for the database. So like when you kind of looking to do benchmarks, when you're trying to find the specific bottlenecks, you want to find out, okay, like should I tune my delete workload? Should I tune my insertion pipeline? Should I tune my updates? So finding this ratio kind of helps you get to that. And then obviously you can get throughput. So what kind of throughputs are you looking for? What kind of guarantees are you giving to your application users? And then what is the database able to offer you? So if you look at the exact commit, you will be able to find out how many commits, how many transactions, and you can reset these stats. So if you want like more accurate numbers for a particular day or something, you can reset these stats and then get them again. So this was for the entire database. Now, generally, this gives you a good idea of where to look for, but it's not enough. Like if I were to tell you, okay, there's a lot of transactions going on in your database, that's not telling a lot. It just tells you that there's some problem with the throughput. You want to figure out, okay, which part of my workload is causing that, right? So there's another set of tables which gives you per table information, right? So it's called pgstat user tables. It has a lot of columns, so it's a bit small to read. But the more important ones here are, it tells you how many times you initiated a sequential scan on that table versus how many times you initiated an index scan, right? And how many tuples each of them had to read. So that's very useful information to kind of determine if you need indexes or not. If you are like, I've talked to like developers at times, they are like, okay, my database should never be doing sequential scans. We don't scan more than 5 rows at a time. And then we go to the database, and the database's picture is very different. So database is always doing sequential scans, because even though you are asking for 5 rows, maybe you don't have an index which tells the database that it just needs to scan 5 rows to get that information to you, right? Other thing it tells you is number of tuples inserted, updated, deleted. So again, similar statistics for a table basis. The number of live tuples, number of dead tuples, that's kind of where the bloat and the auto vacuum comes. So this was a very clean database, so it doesn't have any dead tuples. But that's probably not going to be the case when you run this on your database. The number of dead tuples is basically the tuples which are not going to be used anymore, but Postgres has not gotten to cleaning them up. So that kind of gives you an idea of bloat. So there is, like, if you search for bloat Postgres, you'll get a very complex query. It basically uses like this table and a couple of other tables to give you that information in terms of gigabytes or terabytes, how much bloat you have in your Postgres database, broken down by table, etc. So I didn't want to get into like this exact query. If you guys are interested, I can add a bunch of useful queries to the appendix of the slides, and so that you guys can just copy paste them, run them on your database, and see if that's useful. And then it also shows you like the last vacuum, auto vacuum, last analyze, auto analyze. So as I told you, Postgres has auto vacuum, which comes up every once in a while, and then actually runs vacuum and analyze on your database. What vacuum does is it cleans up that bloat. What analyze does is it captures statistics so that it can use those statistics in the queries. So if you're not running that often enough, if you have a feeling that, okay, like my auto vacuum and should be tuned well enough to kind of remove all that bloat, maybe it's not, and you realize, okay, 17 days, like I've seen databases where like for a year, a table has not been auto vacuumed. And then like the database size is 2 terabytes, you vacuum it, and then it becomes like several hundred gigs, right? So generally this won't happen. This is also an extreme case, but by default, Postgres auto vacuums once your table changes by 20%. So that's the default, which is generally not enough for large databases. So imagine you have 1 billion rows in your database, you're waiting until you have 200 million rows of bloat to actually clean it up, right? Which might not be the case. And dealing with most of the Postgres users I talk to, they have large data. That's why they're looking at Citus. So these problems are very often when you have come up very often when you have large databases. So pgstat user tables, what can you do? Approximate number of live dead tuples gives you a good idea of how much bloat you have. Find out if a table is insert, update, delete heavy. We actually had a user who essentially like over 60% of their workload was updates. And then it was just coming from one statement in the app. They were like, if I had known that this update is the main problem, they were able to reduce their write workload by about 90% by just fixing that part of their app code to do less updates, right? So if you can figure out your expectation from your database on like, okay, I will not be doing that many queries. Sometimes Active Record might be doing queries for you, and then you might not realize that you've written code a certain way, and then it leads to much larger traffic on the database. Obviously, you can look at auto vacuum, auto analyze to figure out like if your table is being sufficiently vacuumed or not. And this I find really useful is the number of sequential scans plus index scans. For transactional apps, sequential scans generally are not that required unless you're doing analytics across the entire data set. So if you see a large number of sequential scans, that should raise a flag. You have similar statistics for indexes as well. So indexes, you have index scans. Like how many times did you initiate an index scan on that table, right? Generally, we run into this when you have a lot of write problems. So you want to your write throughputs are not being met because you have a lot of indexes. You have 15 indexes on your table, and when you go and look at how many of these indexes are being used, you realize like 7 of them are not even being used by your queries. So you're just indexes are always a trade-off between storage space and write throughput and read throughput. And there is a point when it makes sense to actually create indexes at the cost of some slowness in writes. But if you have just indexes on every possible query you can run, that actually hurts your database more than it helps, because it probably introduces a lot of unnecessary writes going on in the database. So that's the most useful thing. So again, it tells you tuples read versus tuples fetched. This was a perfect index, so it's only reading what you need to read. But then sometimes if you're running queries with 3-4 filters and you have indexes only on one of them, so then you will find a difference between these. And if you see that there is an index which is just reading way too many rows than how many it needs to, you can make it a more specific index by making it a compound index of 2 columns or 3 columns, right? So those are the pgstat user indexes things. Now coming back to the problem we were initially solving, which is the cache hit ratio not being good, right? So you can actually use the information in all these 3 tables, and there are more, but I think these 3-4 are the best starting points where you kind of find all the glaring issues, if there are any, and then kind of understand why you had a bad hit rate. So you see, actually I should say application patterns, but so you see database patterns which do not align with the application side. So you think you shouldn't be doing a lot of updates, but it turns out your database main workload is just updates. You figure out, okay, I think this table should be small. I realize, oh, it's too large. I shouldn't have dead rows on this table. So this helps you check your assumptions. You can dive deeper into them and fix them. If there is a lot of bloat, there are tables which are your larger tables, but they are vacuumed very less. You can actually tune auto vacuum to trigger at 2% of changes. So you can say if 2% of my table changes, then trigger a vacuum on the table, right? Which is very useful. We actually recommend about 2% for any large tables, so that you can start with that. You can actually also increase the number of processes auto vacuum is using. So that's another thing you can tune. So maybe auto vacuum is triggered frequently enough, but it's not able to keep up with the rate of change, right? So then you might have to give more cores to auto vacuum to keep up. Maybe you're doing a lot of sequential scans. The problem, if that's the problem, you should create a few indexes. Maybe you have a lot of unnecessary indexes. So I'm not trying to imply do 3 and then do 4 for everything, but like there might be some which are unnecessary, and then you can delete those indexes for good performance. So all of these are more generic, not looking at specific queries, not looking at optimizing specific queries. So this is generally useful to kind of start and then dig into okay, these are the kind of problems. But then let's say you sped this up and you have a good index or a cache hit rate, and you still have slow performance, right? Certain queries are not tuned well enough. Certain queries are still not performing. A particular web page is still slow. So how do you kind of isolate what are the queries which are slow, right? This is like pgstat statements is the answer to that question. And then it's actually like one of my colleagues, Claire, was at FOSDEM, and the most kind of most common advice which was given is essentially to use pgstat statements. So what pgstat statements does is it's an extension on top of Postgres which tracks this execution statistics of all the SQL statements executed by the server. So it actually normalizes the queries and groups them together. So it won't be each and every query which ran, but it will say for all queries of this format, this was the, these are the statistics about it, and we'll get into what the specific statistics are which it exposed. And it's exposed to the user using a view which is surprisingly also named pgstat statements. So you can just query it again like a regular Postgres table and get your stats from it. So what does that view contain, right? So it has user ID, database ID, query ID, and the text of the query, and the number of times it's executed on the database. So you have, let's say this query, let's say one query was slow, but it's executed once every 5 days. That's probably okay. But if there was a query which is where you can save 5 10, 15 milliseconds, but that's executed 1,000 times a day, that's actually more useful for you to kind of optimize, right? So it, in addition to kind of like the times, which is like what is the minimum time this type of a query took to execute, max time, mean, it also gives you standard deviation so that you can understand, okay, maybe 1 or 2 bad occurrences, or is it always kind of performing bad, this query. And it also tells you the number of times it was executed so that you can correlate both those pieces together. It also tells you information about I/O. So there's how many shared blocks were hit, return dirtied, how many local blocks were hit, return dirtied, and also total time spent in reading and writing blocks, right? So let's see a few examples of what you can do with this information. So these are one of few of the most common queries I run on the database immediately is what are the top 10 time consuming queries. So like you notice that I'm using total time, I'm not using one time. So this tells you what is the queries on which your database is just spending most of its time in. Because it's total time, it's actually a product of essentially the mean time times the calls. So that's a good measure as opposed to just looking at calls and saying this is the most common query, but if it executes in a millisecond, then it's okay. Or just using the time for the query, but maybe it's executed very rarely. So this is generally a good measure. Sometimes you find out, like, for example, in the bad cache hit rate example, right? You find out that you're doing a lot of discretes. So what you want to find out there is what are the top 10 queries spending most time on discretes? Because if you see, like in your monitoring tool, you see, okay, a lot of my time is going in discretes. You find only those queries and you tune those queries. Or you just want to go find what are the top 10 most common queries. That's useful when you're doing some kind of a benchmarking, etc. You don't want to benchmark, like you want to benchmark your worst queries, but you also want to benchmark your most common queries. So you can pull all these information to kind of pinpoint your attention at what exactly you should be tuning rather than, generically making optimizations after you have done a good basic set of best practices. This is a query I would strongly recommend to run on your database to kind of find out which are the ones you should be looking at. This is from one of these blog posts on pgstat statements. So it kind of shows you what are the most important things. So it shows you the calls, total time, mean time, max time, and standard deviation time. It also pretties up your query so that it looks nice on the screen and you can easily kind of look at it and debug it. It shows you only queries by the current user. It does that, well, not the current user, anything which is not the backup user. So sometimes like backup things will show up. And then it kind of says, find me the top 15 queries sorted by the average time. So this is generally a good query to run and a good starting point. It displays a bunch of things to you. If you look at this example, it says, okay, the total time the database has spent in this query is about 121 seconds. The mean time is actually 861. The max time is 3 seconds, 3.7 seconds. This is the standard deviation. These many rows are returned from this. So just go and run this on your database. I'm sure you'll find some interesting things coming out from it. Now, let's say you kind of found out what are the queries which are slow. Now, what do you do to tune them? That I think can make several talks and several workshops on its own. But the very basic of it is you start by doing an explain analyze. So you pick up a query, you do explain analyze. What's useful to know, and this is a common thing, like people generally just do explain. And explain gives you just what Postgres thinks of its worldview, but not what might actually happen when you execute the query. So if you look at explain and you look at the cost, it just tells you, and if this was a more complex plan, you would see many more costs, and that kind of Postgres estimates this is going to take this much long, but it might actually not be true at all. So what you want to look at when you're looking at explain analyze is the actual time. So on the right hand side, you see actual time, where it shows you when the following rows were outputted, how many rows were outputted. So this is a very simple query where it's just selecting all the rows where a particular column value is 1. So it shows you it expects to return about 9,584 rows. It returns actually about 10,000 rows. So it's pretty close. The estimates are pretty close. So and then you read the query plan and then you figure out which part of the plan is taking the most time in the actual time, not in the estimates, and then look to tune that. either by creation of indexes or by tuning some other Postgres tuning parameters. Now that's the standard part of, when you do explain analyze, kind of tune the slowest part of your query. But Postgres actually tells you a few interesting things in explain as well. So let's look at this query. So where I'm selecting from a table where column 1 is 1 and column 2 is 0. If you look at this, in addition to just, you can tune the query plan, but you realize that actually there is a discrepancy and a significant discrepancy. It's 100x off in terms of what Postgres thinks this query will return. So Postgres estimates it's going to return 100 rows, whereas actually the database returns 10,000 rows, and that's really off. So if you had anything above this plan, so if you were doing aggregates, if you're doing joins, the plan Postgres would actually choose would not be good, because it believes that only 100 rows are going to come from this scan, but actually 10,000 rows are going to come from this scan. So there is actually like something you should note. I think there is a lot of advice on tuning Postgres and making it like once you see and explain, analyze how to go about it. But then there is something which is very important to consider is the reasons for slow queries is not always that you can add an index and speed things up. Sometimes Postgres may have wrong statistics, or like it has not looked at enough data to kind of get the correct statistics about your data. So if you look at this, the problem is anything which happens after this, it might be very badly, like bad execution plan. And that's not because you didn't create the right indexes or anything else. It's just because Postgres thought that something is going to come from this particular scan, but the number of rows were much, much larger. So the first step when you see bad kind of statistics is to analyze again with a higher default statistics target. That's actually the number of rows Postgres uses to take an estimate of data distribution. So you say, okay, that makes analyze more expensive because now Postgres will scan more rows to kind of get those stats, but it makes the stats much more accurate. So that's the first thing to start. But the problem here is actually not that. And I'll just pick one example of how you can, when you have mismatching statistics, how you can actually tell Postgres to fix its statistics, or how you can tell Postgres to improve its statistics. So the reason there is an issue here is in this particular schema, column 1 and column 2 are correlated with each other. So column 2, actually the value of column 2, I populated the data so I know, but is actually column 1 divided by 10. Right? So there, if you know column 1, it's actually enough to determine the value of column 2. But Postgres doesn't know anything about that. Postgres by default will only capture statistics for a single column independently. So it says, okay, maybe there's going to be 10,000 rows returned from column 1, 10,000 from column 2. Now, both of those filters are going to be applied together, and then maybe I'll just get 100 rows out of it. So it uses the selectivity ratio estimates it has to kind of come up with this number. But then actually, this is not going to produce the correct results irrespective of whatever indexes you add, anything, unless you tell Postgres about this correlation between them. So Postgres allows you to declare multi-column statistics. It doesn't do it by default, because if it were to do it on all permutations and combinations of all the columns in your table, analyze would just take way too long. But then you can tell Postgres two columns are correlated by creating statistics on it. So that's the syntax. For that, like we don't need to get into that, but it says, okay, track dependency statistics of column 1, column 2 on each other. And once you have that information, you can see this is the exact same query. I ran it again after analyzing the table and telling Postgres to kind of capture the correlation statistics. You can see there's a sequential scan. Now it estimates 9,584 rows instead of the 100. And it's much more accurate. So anything which happens after this is going to be much more efficient. So actually, like it seems like create statistics seems very like people don't think it's going to actually make a huge impact. This is actually something I tweeted like last year in July. We had a customer who saw over 1,000 times faster performance, and I know it seems like, oh, I just needed to run this one SQL query to get 1,000 times better performance, but it does happen. Like wrong query plan estimates. Like this is such a simple query. If it were a more complex query, you would have a lot of issues just because Postgres thinks the number of rows are different from what it actually is, right? So to summarize this, like use pgstat statements to find the right set of queries to optimize. Use explain, analyze, and tune the slowest part. Again, emphasis on analyze. Don't just look at explain and assume that Postgres is going to do, like we saw that explain is very different from what actually happens in certain cases. Keep an eye out for differences between estimated and actual to find ways to fix or tell Postgres to fix its statistics, because they may not always be correct. So that's basically the main content of my talk. I added a bonus on quick estimates. So this is something which is not necessarily related to the rest of the talk in terms of like performance tuning and other things, but just using the stats Postgres captures, you can actually get a lot of good estimates about certain things for which right now you might be running very expensive queries to figure that out, right? That is kind of captured in pgstats. So this captures information about each of your column and what Postgres thinks about it, right? So if you look at this, it tells you the null fraction to start with. It tells you number of distinct values. Here it has a fixed number of distinct values, so it tells 1,000. Sometimes it tells you ratios. So it can tell you, okay, 20% of your table is going to be the number of distinct values, right? That's useful to understand sometimes. The ones which I find most interesting and I write up my Hacky scripts using is most common values and most common frequencies. So for doing estimates for, okay, like let's say your top 10 customers, you will actually find good estimates from them in the most common values. So you will say, okay, the most common values are these, and the number of rows I have for this customer are going to be, let's say, in the most common frequencies. So what this is actually saying is for the value 945, about like 0.0017 into the number of rows in the database is how many rows that particular ID has, right? So you can use that for like just basically approximating, like let's say you want to find out, let's say you have a table of network bytes and you want to find out which devices are actually giving the most amount of like bytes, which devices kind of are emitting the most amount of bytes. You would write a complex, even if it's not complex, it's definitely expensive, a count distinct kind of a query to figure that out. I would just go here, check if Postgres has statistics on your top 10 devices, and then just use that to figure out, okay, how many packets went through the system? Well, Postgres has an estimate for that. I can give you a rough ballpark. These are the things you can do in one of 21,345,000 results. You don't need to actually tell them what is the exact number. You can say about these many, right? So the other kind of useful statistics is you get histogram bounds as well. So if you have certain assumptions of how you can, how your data is supposed to be spread out, you can actually confirm that. So the approximations I use this for is what's the null ratio for a particular column. What are the approximate number of distinct values for a column, right? You saw that you don't need to do a count distinct necessarily to kind of figure that out. You can just look here and get a rough idea of what that is. And then what's the most common values for a column, and what are the approximate number of rows which have that. Approximate count. So this is another thing which I generally go and run. Like if you have a very large database, Postgres doesn't cache your count star. So like people expect count star to be a very inexpensive query. It's not in Postgres. It actually needs to scan your entire table to count each of the rows. So I don't like to do that when I have a billion row table. So I just go to this and get a rough ballpark of, okay, how big is this table? What kind of operations can I even try to do at this table? Right? If I see, so you can just go to, there's a table named PG class. You can just go there, find the rel tuples, which is Postgres' estimates of how many tuples that has. So to summarize, Postgres exposes quite a few stats to you. In this talk, we've mainly covered performance-related stuff. What kind of places do you want to look into for performance issues? Like what are the kind of pointers which point you at things to dig deeper into? PG stat tables generally help you find which indexes, statistics about indexes, tables, IO statistics, vacuum statistics. PG stat statements helps you find your slow queries. Use explain, analyze, or actually even better is explain, analyze buffers to kind of see what kind of IO it's doing. So it tells you how many, like for this query, what was the hit ratio and how many of them were to fetch to be fetched through disk. And then lastly, you can use pgstats, pgclass to get good approximation and understand what Postgres understands about your data, right? So I have one last thing to say. So if you have not heard the news, Citus Data was acquired by Microsoft. So we are actually working on like launching Citus on Azure. If any of you is interested in kind of seeing when Citus is going to be available on Azure, you can just go to this link and express interest. We'll just keep you in the loop on that. And then that's my talk. And I have 2 seconds remaining, so I was right on time.